Thank you, Chantal. I will start with a short detour in time back to 1992. This was the first IBC in Amsterdam, and at that IBC, the Scandinavian Wideband project, which I happen to be the project leader of, demonstrated for the first time with a hardware demonstration HDTV over DTT. We had the slogan, "One big step for television." We wanted Europe not to take small steps improving the analog variants that was the mainstream at the time. We wanted to promote one big step going to all digital. Actually, this demonstration was enormously successful, and it was not the only reason, but I think it contributed to the creation of DVB in 1993. The rest is history, is a common expression. Now, going back in time to today, the situation, we have taken a number of smaller steps after we took the big step to digital, and now it is painful to migrate to new broadcast standards. There are some improvements that have been identified, but normally not considered big enough. It's difficult to justify a new, let's call it DVB-T3 standard without radically improved performance and functionality. We have also an uncertain spectrum situation. So a small step is not enough, it seems clear. So perhaps it's time for a big step again, or why not a giant leap? And let's see if you have the same association as I have with a giant leap. Yes. Neil Armstrong also said with a tongue-in-cheek. Now, to see whether this is possible, we start with looking at traditional frequency planning. It looks like this. If this is a large area with a number of different transmitters having different frequencies, the frequencies are reused according to a certain pattern. And in this example, we have a reuse 7. So 7 frequencies are used, but only 1 can be transmitted from each site. So only a fraction of the UHF channels are actually used from a given site. But what about SFN? Isn't it reuse 1? Yes, it is within the SFN, but all SFNs have borders to other SFNs, so where you have to reuse the frequency. So you have basically something like reuse 4 also for SFN. Another important topic to consider is the well-known Shannon's law regarding basic communication and the required power. It stipulates that capacity is proportional to the signal-to-noise ratio in decibels, which is the logarithmic measure. So required power increases exponentially with capacity, which is not a good thing if you want to transmit a lot of data. High capacity also means high sensitivity to interference, which also needs to be considered. This is how it could look like from a normal DTT station today in principle. So you have a huge power on some frequencies and no power at all on other frequencies. Extremely unbalanced. On those frequencies where you transmit, you are very far up on this exponentially curve on required power for capacity. This is very bad from the efficiency point of view. It's bad for capacity and it's bad for power. And earlier studies that we have performed shows that you can get higher capacity and lower power consumption with a lower reuse factor. So then we thought, what about reuse 1? And this is WiB. WiB is going to reuse 1 and spreading the power equally over all frequencies. So you see again in dotted lines the existing situation, but with WiB with far lower power. Actually, you can transmit with 7 dB difference per RF channel, which is a factor 50 in power. And but you use all the frequency instead, so you have a net gain of 90% of transmitted power, and you get about the same capacity in this way, and the same coverage. We will see later you can also extend the capacity quite significantly. Basic principles of WiB then, it's wideband of course, and it's wideband in a few different senses. It's wideband from the transmission point of view, since everything can be transmitted as a single WiB signal, covering potentially the whole UHF band. Reception, it can be done with what I call a narrow wide tuner. So it's wider than today's tuner, but it's much smaller than the total band, so perhaps 32 megahertz. It allows for high service bit rates, also using robust transmission modes. The tuner would be frequency hopping around the whole band, so you would have wideband frequency diversity. Then second principle is the reuse one. And of course, adjacent transmitters then use the same frequencies, so you have a very challenging interference situation with carriage-to-interference ratios in the order of 0 dB, and we will come to how that is handled. Robust transmission mode is required, and interference cancellation methods. They are, let's say, inherent parts of the WiB concept. So sometimes I get the question, what does WiB stand for? So I think wideband reuse 1 is a possible explanation. Then how to handle interference. So irrespective if you have a kind of a traditional high power, high tower without SFNs, or if you have SFN areas, it can be handled in the same way. And you have three basic tools here with WiB. So the first one is to use a high basic robustness. Second one is to use the receiver antenna, and then we distinguish between two cases. The rooftop antenna case, where you have normally today also a directional antenna, and the normally assumed antenna discrimination according to ITU is up to 16 dB, depending on the direction, of course. For the mobile case, you don't have a directional antenna in the normal sense, but you can imagine having dynamic beamforming with smaller antennas that are used in an intelligent way. We'll come back to that in a moment. And finally, you have interference cancellation methods, which is the third method. So then interference cancellation, how does it work? We consider again three transmitters here, TX1, TX2, TX3, and you have the receiver in the midpoint. So it's, let's say, a worst case situation. And we assume that the required C over N of the system is 0 dB, which means in linear terms 1. So the power must be larger than the noise or interference. Suppose the received signal in the midpoint consists of components from all these three transmitters. You order them then in size. So you start with the trick is to start with the strongest one. So we call it C1 here, and then C2 and C3. Suppose that C3 is the real one that you really want to receive. You start anyway with C1, and you demodulate it, and you can demodulate it if the C over N requirement is fulfilled. You can then it is a known signal, so you can remodulate it and cancel it. You can subtract it from the signal. That's exactly the same kind of technologies that Jan talked about. It's LDM. Then you can do exactly the same step once again, but based on the TX2 signal, and remove it in the same way. And then you have the TX3 signal, and you can, which is just limited by noise, and you can demodulate it. Sounds like magic, but it works. We have no hardware yet, but we are sure it works from theoretical point of view. And there are also in ATSC, they have hardware there. You can see it here at the IBC. Regarding the beamforming, this can be combined with interference cancellation. So if you have a smart antenna that could have an antenna diagram, for example, on the upper right corner, it's easy with signal processing to rotate this antenna diagram. So if you have two transmitters to consider here and you want to cancel one, you can move the antenna diagram in such a way that one transmitter comes into the null of the antenna diagram and is therefore cancelled. Sometimes it's actually better to maximize the C over n plus I, so you find some kind of global optimum, because you can sometimes have a noise penalty by just always canceling the particular transmitter. And what you can do with this antenna processing in each of these 3 steps separately, so it's a very powerful technique. This requires that all transmitters are synchronized, similar to an SFN, but with different content in this case and pilots. The content doesn't have to be different, of course, with WiB, but it can be different. Regarding receiver complexity, it's very important to emphasize that the receiver is not expected to demodulate the whole supermax. It rather extracts a selected service and demodulates only the associated part of the signal. But what we do have in increased complexity is a factor 4 increase in sampling frequency and FFT size due to the wider tuner bandwidth, assuming 4 UHF channels is the width. We have some small but rather marginal complexity increase for the frequency hopping tuner. This has been researched earlier in DVB in connection with T2 and NGH. We also have a significant additional complexity for interference cancellation, but it is fairly limited thanks to all transmitters being synchronized. You can also, in principle, perform interference cancellation in a more general case, but when the transmitters are synchronized and they're using the same system and so on, things can be simplified a lot. We have performed network simulations on such a network with hexagons, and there are a lot of assumptions here. You have them all in the paper. I will not go through them here, but this can simply be explained as a high power, high tower network using a receiver, a rooftop reception antenna, directional antenna, in the worst point in the center between 3 hexagons. We consider actually for the performance 2 cases here, one which we call best transmitter and the other is the wanted transmitter. So if you're happy of receiving any of the adjacent transmitters, which may be the case if they transmit the same content, which they may very well do, or if they transmit regional content and you can survive receiving any of them, then that's fine. But it could also be at the country border, and then it's not okay. You need to receive a particular transmitter. So the wanted TX case, it is, okay, we want to receive precisely this transmitter. It doesn't matter the quality of the others. This is the one that we need. So of course this is more critical. So in the lower table you see the spectral efficiencies that can be obtained with these 2 cases, and the best TX is dramatically higher, but the critical wanted TX, this is probably more a common figure, the common assumption. And with DVB-T2 today you can get about 1 bits per second per hertz. And somebody here may think about 256 QAM, this is not 1 bits per second per hertz, but you forget then the frequency reuse, that you only use 1 frequency of 5 frequencies, so you have to divide by 5, so you end up with something like 1 bits per second per hertz. We have also performed system performance simulations. This is quite interesting. All the network simulations have treated interference as noise. This is a common assumption, but actually, and if it is treated as noise, then there is no tolerance for noise when the character interference ratio is 0 dB for this spectral efficiency, 1 bits per second per hertz. No, it's theoretically impossible. However, the interference is not noise. It's QPSK, for example, and then the constellation is known, and you can exploit that fact when demodulating the signal. And this allows actually QPSK with a 0 dB interference level to be demodulated at 6 dB C over N instead of infinity, which is a huge advantage. So we haven't included that yet in the network simulations, but are planning to do so, and we expect further performance increase in the network simulations in this way. This is a bit complicated diagram, but what it actually shows is on the right, or on the horizontal axis, the C over n, and on the vertical axis, the C over I. So you have all the points here are all the possible combinations of C over n and C over I. And on the red lines here, sorry, the white lines, you have the combinations of C over I and C over n that is needed for a particular spectral efficiency. As an example, then, this 6 dB point is here. So you are on the vertical axis at 0 dB C over I, and you are on the horizontal axis at 6 dB C over n. And the white curve is the one with 1 bit per second in hertz. And you can see that you can go up quite significantly in capacity at the cost of noise, of C over n, sorry, but still with a C over I of 0 dB. We have also tested this. This is with real ATSC codes, and been able to show that such processing behaves close to the ideal method. Another topic, statistical multiplexing. This has nothing to do with RF aspects as such, but the transmission system may have imposed limits on StatMaxing. So with WiB, StatMaxing may be performed over a StatMax pool consisting of up to the capacity of the entire WiB signal, which could be then 200 to 300 megabits per second within the whole band. And StatMaxing, I assume most of you know what it is, but it's a way of combining video-coded services within the constraints of a total capacity. The higher that total capacity is, the better it is. And the more services that you can combine, the better. So this huge StatMax pool could allow even for close to ideal StatMaxing of UHD services. Reduced costs is a very important area where WiB offers big advantages. For the CapEx, the capital expenditures, we first note that we could use a single wideband transmitter for everything within on one side. And the required output power from that transmitter would be about half of one existing transmitter. There wouldn't be any need for combiners because you don't have anything to combine. You only have a single wideband signal, and so you would need a single wideband RF filter. So this is what a combiner room looks like today, an example, and you could simply get rid of that. Thanks to the lower equipment volume and weight, it may allow mass positioning of the transmitter. So in that case, you wouldn't need any RF feeder either. And the lack of RF feeder and combiner may in total help. Could reduce the total attenuation in this chain by maybe 3 dB. So you would have another 50% reduction of the power just by that. You could have lower performance requirements on the transmitters due to robust transmission, and drastically reduced need for cooling and backup power. And regarding OPEX figures, you would have much less energy consumption, reduced maintenance needs, and no need for frequency planning. Introduction scenarios, there are two different approaches, the dedicated band approach and the interleaved approach. I see I have little time, so I have to go a little faster now. In the dedicated band approach, one would introduce WiB in a similar way as with 8 and 7 megahertz band introduction, but with a WiB subband, which would have coordinated introduction, and in the long term, the full band could be used for WiB. In the interleaved approach, you could introduce WiB together with existing DVB services, and WiB would be transmitted with a low power, and if necessary with the opposite polarization to improve performance. Some extension possibilities of the WiB concept. One is the cross-polar MIME, where we would have both polarizations at the same time. This may further double the capacity, and this could actually with WiB be backwards compatible with the legacy antennas, thanks to the large antenna discrimination. The most important is perhaps the LDM-based combination of broadcast and unicast in the same spectrum, where the same time and frequency resource block, if you like, could be transmitted on both layers with controlled power difference and separated by interference cancellation. So instead of this prolonged tug of war, if you like, we could have, why not this win-win peace project where DTT and mobile telecom would share the full spectrum, but in an LDM way, with one on top of the other. So there would be a control level difference. The mobile telecom signals are invisible for DTT receivers. They would be separated via interference cancellation, and the mobile telecom receivers would first demodulate and cancel DTT. So WiB vision could be to have the same standard for broadcast and unicast. So to summarize, WiB could offer increased spectral efficiency, radically reduced cost, unconstrained use of local services thanks to the interference cancellation, close to ideal StatMax gain also for UHD, high-speed mobile reception thanks to the robust mode of all services, no need for dedicated mobile services, commercial acceptable introduction scenarios, and a converged win-win solution with mobile telecom. So is this a big enough leap? If this is feasible, we say yes. And we would like to invite everyone to join our forces and continue to study and evaluate and develop the WiB concept. For more information about WiB, you can see the Terracom webpage, and also go to here at IBC to Progera Radio Combination in Hall 8. Thank you for your attention.